Last class we have discussed some parameters of the free electron theory at absolute zero temperature. Today we would like to find the effect of temperature on that parameters. So first we would like to discuss about the Fermi energy EF at elevated temperature. We know that the total number of electrons could be found by the expression as n equal to 0 to infinity dE Fe dE. And if we write the explicit form of Fe, then n becomes 0 to infinity dE 1 by exponential e minus ef by kBt plus 1 into dE. So now we have to evaluate the above integration for Ef because we want to find out the Fermi energy level at an elevated temperature. We will follow the general procedure for such an integration form. So our task is how to evaluate this integral. First, we would like to evaluate the integral of the form I equal to 0 to infinity Fe dE of Ge dE, where Fe is the Fermi function. So we would like to evaluate this integration, that is n equal to 0 to infinity dE Ge dE, and we will find this integration from this form. So first we would like to evaluate this integral I equal to 0 to infinity Fe G prime dE, where Ge is any function such that when e tends to 0, Ge tends to 0. So now our integral becomes I equal to 0 to infinity Fe G prime dE. And if we evaluate this integral by parts, as we know, the integration u dv is uv minus v du. So we will use this formula to evaluate this integration. So let's see. Then I becomes Fe Ge, and the limit is 0 to infinity, and the second part is 0 to infinity Ge f prime dE. But as we know, when e tends to 0, Ge tends to 0, so the first part of this integration becomes 0. Hence we have to evaluate this part only. So now to evaluate this integration, that is this part, first we would like to expand G in terms of Taylor series, and the Taylor series expansion will be about EF. So now Ge becomes Gef plus G prime Ef by factorial 1 e minus Ef plus G double prime Ef by factorial 2 e minus Ef whole square. Now substitute this expression in the integration. So this is our actual integral, that is minus 0 to infinity Ge f prime dE. Now we will substitute the Taylor expansion of Ge, and the integral becomes 0 to infinity Gef minus first order derivative of Gef e minus Ef plus half G double prime Ef e minus Ef whole square and f prime dE. And if we rearrange the terms, we will get Gef out of the parenthesis, and inside the parenthesis is 0 to infinity with negative sign f prime dE. The second term is G prime Ef minus 0 to infinity e minus Ef f prime dE, because this is constant, it is a function of Ef, and Ef is a constant energy, so we can take it out of the integration. And the last term is G double prime Ef minus half 0 to infinity e minus Ef whole square f prime e dE. So our integration becomes I equal to L0 g of EF L1 g prime EF plus L2 g double prime EF. What is L0? I have termed this part as L0, that is L0 equal to 0 to infinity with negative sign. F prime EDE, L1 is this part, that is minus 0 to infinity E minus EF, F prime EDE, and L2 equal to minus half 0 to infinity E minus EF whole square F double prime EDE. So we have to evaluate these integrals to get the standard form of I. Hence, we must know what is the characteristics of f prime e function, because it is the first derivative of Fermi function. So let's check what is the properties of the f prime e. So if we draw the fe function at any temperature, and in the same curve we can also draw the f prime e. As we know that if this is the energy axis and the y-axis, first we will draw the Fermi function, and we can see the Fermi function is like this. For any temperature which is above the absolute zero temperature, so this green curve shows the Fermi function. But if you want to plot the f prime e, actually this f prime e will show you the negative peak. But if we want to draw the f prime e along the positive direction, so then it will gives us this type of curve, and this is actually minus of f prime e. This is minus of f prime e, and we can observe from here that f prime e is large only at the energy near EF. It has a peak value only near the energy of EF. It is negligible for other values of E, for negative values of E, because we can see along the positive side it takes a peak value at a certain positive value of energy. So if we go to the negative side, this f prime e shows the zero value. Hence, we can neglect the f prime e values, particularly at the negative value of e. So the lower limit of the integrals may be replaced by minus infinity. In this integration, we have seen the lower limit was 0, but if we use the minus infinity as the lower limit, there will be no problem, because at the negative side f prime e gives you the 0 value. So we will use this intuition concept. Now L0 becomes minus infinity to infinity f prime e dE, and to write this f prime e on the positive side of the curve, so we can write it as minus f prime e dE, and it gives you fe minus infinity to infinity, and it is 1, because fe is the probability of the energy level E to be filled by electrons, and when we are taking minus infinity to plus infinity, this probability function must be 1. So L0 becomes 1. Now the part is for L1. As we know, the expression for L1 is minus infinity to plus infinity with negative sign here, E minus EF f prime e dE, and we can see this integrand is an odd function. So over this limit minus infinity to plus infinity, L1 must be 0. So next move to the L2 function, and L2 is minus half minus infinity to plus infinity e minus ef whole square f prime e dE. If we substitute e minus ef by kbt as x, then dE becomes kbt dx. So L2 becomes kbt whole square by 2 integration x square e to the power x dx divided by 1 plus e to the power x whole square. And if we take the help from standard integrals, L2 becomes pi square by 6 kbt whole square. So we have found out what is L0, L1 and L2. Now our standard integral becomes, which is I equal to L0 GEF plus L1 G prime EF plus L2 G double prime EF. So I equal to 0 to infinity Fe G prime E dE. This is our actual integration, and it becomes, since L0 is equal to 1, so it is GEF only, and L1 is 0, so we can neglect this second term, and L2 equal to pi square by 6 kbt whole square G double prime EF. So this is the standard form of the integration, and on the basis of this standard integral we will deduce our required integration. So now we will use the standard integrals to evaluate the following integrals.